we're going to do, I shouldn't have to adjust the schedule. I'll just look at the problems for the final set of triple integral today, and we'll work through the vector field problems tomorrow. So just look right at the problems. What we're given here is iterated integral. We just want to evaluate it. And you should notice that in rectangular, this is not possible. So we're going to convert it. Probably the easiest one to convert to would be cylindrical here. Remember, cylindrical coordinates, set of order triples are theta z. We look at, I'm sorry, I'm not using cylindrical here. Look at the wrong problem. Spherical is definitely the easiest. Rho theta phi. Remember, rho is distance from the origin to the point. That's clearly 0 to 7. Theta is the angle from the positive x-axis that the projection of the point makes. So it's just the standard from polar. Let's see, if we look at the outer, x is 0 to 7, so x is non-negative. The inner represents y, that's both positive and negative. So we go, okay, well, where is x non-negative and y can be anything? That is quadrants 4 and 1. Theta would go minus pi over 2 to pi over 2. I notice I'm using this convention instead of trying to keep it between 0 and 2 pi. If we did that, that would require two separate integrals. 0 to pi over 2 and then 3 pi over 2 to 2 pi. Phi is our angle of declination. Middle is z. Z is anything positive, negative. And so our phi can range over its entire set, 0 to pi. Just so I don't have to rewrite the integral, I'm going to call it pi. The customary order, d rho, d theta, d phi, or d phi, d theta, sorry. So innermost is rho, middle would be phi, outermost would be theta. Convert the integrand into spherical coordinates. Square root of x squared plus y squared plus z squared is the distance from the origin to the point, which by definition is rho. Now for dv. dv is rho squared sine of phi, d rho d phi d theta. Again, the most common mistake, as with polar, is forgetting that additional term, rho squared sine of phi, in the conversion. Simplify, there is the iterated setup. And just to show you quickly, that would be Fubini's theorem of spherical. Well, look, there's no theta, right? So we just go, okay, well, that outer integral, what's its length? Pi over 2 minus negative pi over 2. Just pi, right? I think what I'll do here is use that property that says, well, look, our integrand is function of strictly rho times function of strictly phi. So the double integral is the product of the two single integrals. Antiderivative for rho is rho squared over 2, right? Antiderivative for sine, negative cosine, right? Rho squared from 0 to 7, 49. Cosine phi, what is cosine of pi? It's cosine of pi. What's cosine of 0? That evaluates out to negative 2. -1 minus 1, -2. We're left with just 49 pi. We're going to integrate square root of x squared plus y squared over the solid bounded by the circular paraboloid z equals 1 minus x squared minus y squared and the xy plane. Equation for the xy plane would be what? What's the equation of the xy plane? Pop quiz, what's the equation of the xy plane?
And what exactly?
Just what's the equation for the xy plane?
Y equals mx.
That's a line.
Can I get a hint?
It's obvious.
Can't be that obvious.
1 equals 0.
Y equals right?
Z equals 0. And it's obvious because the xy plane is at a height z equals 0. It's just x and y. Just like the xz plane would be y equals 0, right? And the yz plane would be x equals 0. I had 2 days of rest, so I guess I wouldn't really call it rest, but
The outside attendance wasn't on the floor.
yeah, I've been doing it on the slide. So once I get back to the slide, you see the QR code. Where do I want to go from? 1 to whenever you want it to be. Yeah, nice 5 to 5 looks good. This one, off the mesh. box, set origin, the actual origin. Should work. No, they don't want that. Whatever. Right, so the region we're looking at, our solid, is bounded by the paraboloid, right? I'm just going to go on my point, right. So it's going to be above the plane and below the paraboloid. So it's definitely going to be, I don't need C to go -5 to 5. If I use 0, am I still going to get the plane? I am. Excellent. And we can now shrink the other viewing window to -1 to 1. And I can probably get Z to go 0 to 1, like that. And let's just try and get this to be a little diagonal. Something like that. Should be good. That's the viewing. So now we have an idea of what the solid is, right? Save. And there's your QR code up there. Okay, so now we need to describe that region. We need to describe that solid. Okay. Pleasure. Thank you. New. That was going to get cut off. Okay, so it's time to adjust that. Oh, okay, that's good. I just have to move it up. Yeah, that's pretty good. Now we have to decide our coordinate system. Rectangular is not going to work. I guess maybe it could. No, it doesn't look like it will. We're going to go to do the z, no problem. But then you're going to be left with the quantity of 1 minus x squared minus y squared times that square root, and that is not going to work in rectangular. So we're just going to skip rectangle altogether. Well, pop quiz. Since you're late, pop quiz. What coordinate system should we use for this integration?
Polar.
What is it?
Polar?
No, it can't be polar. But, you know, give it 75%. So it's close. Cylindrical. It can't be polar because it's a triple angle.
Oh, okay.
But cylindrical is the three-dimensional equivalent. So you get 75% credit for that. Here you can tell that cylindrical is going to be the easiest. Because we're dealing with, if you look at the projection on the xy plane, a polar region that has height. So clearly cylindrical. R theta z. Again, z is the same z, right? That doesn't change, so that's the easiest one. R is distance from the origin to the projection of the point on the xy plane. And theta is still your standard theta. Right? It's the angle that the ray of O, P prime is the projection of the point, makes with the positive x-axis. So basically it's just look at that curve of intersection. R theta is just that domain described, right? Which is a unit circle centered at the origin. There's your r theta. Radius is 1, it's the entire circle, 0 to 2 pi. For the z, definitely going to go from 0, right, the xy plane. And it goes up to the orange, the paraboloid. 1 minus x squared minus y squared, but write that in cylindrical. What is it? 1 minus r squared. There's the description of our solid. Standard order, conventional order for a cylindrical, dz, dr, d theta. Theta on the outside, here, we can do it, right? R is not dependent on theta, theta is not dependent on R or Z. In fact, Z is only dependent on R, right? So Z has to be done before R. The other two you can do in any order. So we're going to say the middle one is R, the outer one is Z. Now write the integrand in terms of cylindrical. So square root of x squared plus y squared is what in cylindrical? Which is what? Just R. dv in cylindrical, r, dz, dr, d theta. Same as polar. The extra term you get when you convert your differential into cylindrical is an r. And again, that is the most common mistake. There is our iterated setup for this integral. Now it's just a matter of evaluating it. I can do two steps at once here. No theta anywhere. So I can just integrate with respect to theta and say it's the length of that interval, which is 2 pi. There's also no z in the integrand. Once again, I can then just integrate and say it's the length 0 to 1 minus r squared, which is 1 minus r squared. That is what we're left with. Which is a very simple integral. Antiderivative for r squared is a third r cubed, but r cubed from 0 to 1 is just 1. And then using the same argument for r to the fourth, it's 1/5. What's a third minus a fifth? What is it? And then just multiply that by 2 pi. 4 pi over 15. I'm going to go ahead and integrate x squared plus y squared plus z squared over the ball of radius 2. Ball of radius 2 should be obvious. The best coordinate system to use spherical. sphere. A solid sphere. Radius 2, phi goes 0 to 2, and it's the entire sphere. Theta goes 0 to 2 pi. Phi goes 0 to pi. Theta first, or theta last, so outside is theta, 0 to 2 pi. Middle is rho, 0 to pi. Innermost, I'm sorry, phi, and then innermost is rho, 0 to 0. Convert your integrand into spherical. What is x squared plus y squared plus z squared in spherical coordinates?
Is it rho sine sine phi cosine phi squared plus rho sine phi sine theta squared?
Oh, you're doing way too much. Simplify that. It becomes a lot easier.
This is just rho squared.
It's just rho squared.
Oh.
And now the differential. Rho squared sine of phi, d rho, d phi, d theta. There's no thetas anywhere, and rho is not dependent on phi. Integrate with respect to theta first, you get 2 pi. If you integrate with respect to phi, we already did that integral. Integral from 0 to pi sine phi is -2. No, it's not. I'm sorry. It's -2. It's +2. That's a useful integral to remember. Because as you see, it's probably going to show up a lot in spherical integration. That just saves us time. One-fifth row to the fifth. But that's from 0 to 2, which is just 2 to the fifth, right? 2 to the fifth over 5. What's 2 to the fifth?
2/3.
And then times 4. 120. And 25 over 5. So far, so good. Volume of the solid enclosed by the two paraboloids z equals x squared plus y squared, and z equals 8 minus x squared minus y squared. Well, my options are going to be the same, so just copy paste it. I'm only going to have to change two things. Right, the equations that we're graphing, the surfaces we're graphing, and the viewing window. First one was z equals x squared plus y squared. Second one was z equals 8 minus x squared minus y squared. Let's start minus 5 to 5. I guess all the way around and then see what that gives us. Not good. Let's just zoom out. Start and then adjust. Okay, that gives us at least a better viewing window there. The solid we're looking at that pill shape there, right? Zoom this. Maybe on the Y. Zero to 3. I'm sorry, minus 3 to 3. For the Z, maybe minus 5 to 10. And what about the X? I'm going to keep it the same as the Y. Minus 3 to 3. don't care about that funkiness. All I care about is that middle bit. Yeah, that should work. So first thing I'm going to do is get this. That on there. Okay. We look at this. What would seem to be the best coordinate system to use? Cylindrical would be the best. I'm going to change the viewpoint now. Be from above. So now we're just kind of looking down on the XY plane. A two-dimensional domain, the curve of intersection is a circle. Cylindrical, clearly your best bet. You have a polar two-dimensional domain with height. The height is easy enough. You know what Z is going to go from. Z is going to go from the orange paraboloid up to the blue paraboloid. Right? So lower bound, upper bound. Of course, we're going to have to convert these into cylindrical. R squared 8 minus R squared, right? Theta is also easy. It was the entire circle. R is also relatively easy because it is a circle, it is a true polar region, it's a circular region. So R is just going to go from 0 to whatever the radius of the circle happens to be. But what's the radius of the circle? It's 2. How do you get 2? Set your 2 equal to each other. Solve for x squared plus y squared. You'll get x squared plus y squared equals 40. Gives you a clear radius of 2. Volume of the region is, or volume of the solid. Remember, it's just the integral over the solid dV. There is the iterated setup. Integral from 0 to 2 pi, integral 0 to 2, integral r squared to 8 minus r squared. R, dz dr beta. Both integrating with respect to theta and z are fairly simple.
Do you have to write that R, dr, dr,
Hmm?
I said, are you missing the R?
No. That r is from dv.
Oh,
Now remember, we're not integrating any kind of function, we're just integrating the volume differential itself when finding volume. When we integrate with respect to theta, we're going to get just 2 pi, because there's no thetas anywhere. Right now, the bounds are dependent on theta. When you integrate with respect to z, you'll get 8 minus r squared minus r squared, right? Which is 8 minus 2r squared, isn't it? Let's factor out 2 as well. Antiderivative of 4r is 2r squared. R squared from 0 to 2 is 4. Right, so 4 times 2 is 8. There's 4r integrated from 0 to 2. It's just 8. R cubed, antiderivative, r to the 4th over 4. R to the 4th from 0 to 2, 2 to the 4th, which is what? 16 divided by 4. There's the volume, 16 pi cubic units. And all of these have been fairly straightforward integrals. You can easily do by hand. Remember, unless you're specified that you're not allowed to, you can just integrate with the calculator, which makes it even easier. This one's fine. Without using geometry, we're going to find the volume of this ellipsoid. It's going to be a triple integral. Remember, volume, integrate over the solid, dv. This was x squared plus plus y squared plus 6z squared is equal to 100. And let's just start minus 10 to 10 all the way around. Of course, it's only the one solid, so it's not going to give me a legend. If I wanted the legend, I could cheese this. If I do this, I think it's just going to happen. Yeah, it's going to do that, which is annoying. Type it in. Client use map out. So, squared plus 1 squared plus 6 squared. So I could cheese it so I can just get the expression up there. Now let's look at this. Again, I'm going to kind of rotate this a little bit. Oh, it's going to give me that square there. That's actually annoying. Can I get rid of that? It's not boxed. Show me the options. I can. Looks like I can. That's it. Let's put it in here. Boundary style. Automatic. None. Uh-oh. Yes, it is. Let's do this. There we go, boundary style. There we go. Now no more hideous box. What coordinate system is going to be the best?
Spherical.
Hmm?
Spherical.
If you're going to do spherical, what does rho go from?
0 to 2 pi.
No, rho's distance from the origin to the point. So it goes from 0 to
The function.
write that in terms of spherical and solve for rho. I'll get started. This is rho squared sine of phi. So you have rho squared sine of phi plus 6 rho squared cosine squared of phi. What's rho squared then? 100 over sine squared of phi plus 6 cosine squared of phi? So rho is the positive square root of that. I go from 0 to square root of 100 over sine squared phi plus 6 cosine squared phi. Now you get to integrate that with respect to phi.
So now it's spherical.
Oh, right, actually, because it's rho squared. There's actually going to be a rho squared in there, so it's rho cubed over 3 from 0 to that. So it would be that cubed times sine of phi. And you get to integrate that with respect to phi. Have fun. Spherical is not your best option here. That only leaves one other. It's clearly rectangle was not going to be a suitable option.
Cylindrical.
It's got to be cylindrical. The xy plane, your r theta, is just a circle, isn't it? That leaves us only with a height. Right, bounds for z. And just the bottom to the top. Right. We're starting to solve that for z, by the way, but at least now it's in cylindrical. X squared plus y squared is r squared. 6z squared is 100 minus r squared. Z squared is 100 minus r squared all over 6. Which means the absolute value of z is the square root of that. Z goes from negative square root to positive square root. little bit. But I don't feel like writing that square root too many times. Somebody's not happy. So for now, I'm just going to say let big Z equal that. Okay. Z goes from negative big Z to positive big Z. Theta is 0 to 2 pi. That's the entire circle. And what's the radius of the circle? 10. What was 10? That's easy enough to see. Just let Z be 0 in that equation. X squared plus y squared is 100. That would be the iterated setup. Integrate with respect to theta, you're going to get 2 pi. Integrate with respect to z, it's going to be twice capital Z. Oops, I forgot my R. And that is a use of. Not, sorry. 8. 2. Divide by 2, not multiply by 2. Obviously, your u is going to be what's under the square root. Derivative of that is negative 2r. So you have to multiply by minus 1/2. Antiderivative of square root of u. Two-thirds unit of 3/2. That will be evaluated 0 to 10 for R. Get a negative 4 pi over 3. Times. Plug in 10 for R, you're going to get 0, right? Minus, plug in 0. You get 100 over 6 to the 3/2. And of course, it's a minus that, so negative. 100 to the 3 halves. 10 cubed, which is 1,000. Six to the 3 halves. 6 squared root of 6. And you want 6 to the 3 halves. 3 halves is 6 root 6. So what's happening there? And you'd be right. That you'd be right. That's a U sub. So it does go away, right? Negative 2r. So we multiply by minus 1 half, so you're going to have that r dr. Should be 4,000 pi over 3 root 6. Check that. Zero, 200 over 6. Over 3. Plug it into a calculator. So I screwed the arithmetic somewhere. So you should get 500 root 2 over 3 root 3. And then you rationalize it. No, that's not right. I'm going to stick with that calculator. Screw with the arithmetic somehow, I don't know where. Unless my notes are wrong, which is a distinct possibility. If you multiply 3, it's going to be what? 2,000 pi root 6 over 27. You rationalize. Or if I get rid of that, root 2, (4,000 pi over 9 root 6). Which maybe is what we had originally, I don't know, but that's from the calculator. So that's what I'm going with. The project is due tomorrow. Right, the hyperspheres. And this web assigned homework will be due next Thursday. Look at vector fields tomorrow.